Alright, so we've got a region here in space, and we've got a function of three variables, and we want to figure out how to set up the triple integral of this function over this region. So this is region R here. The triple integral over R of f of x, y, z, dv. Okay. Now we're going to set it up as an iterated integral, so we're going to do one variable at a time. And essentially what we have to do is we have to look at how does this thing project down to each of the coordinate planes and then make our decisions here accordingly. So if I just took a light above it and shined straight down onto the xy plane, it's like what would the shadow of this region look like? Or maybe I want to shine my light parallel to one of the other axes and maybe look at what it looks like over here, or maybe look at what it looks like back behind, uh, shine my light parallel to the x-axis here and look at what it looks like back behind there, and it's going to be back in behind. And depending on which one of these is sort of the easiest to use, will determine how I set this up. Now, as you can see, my pictures become very tricky very quickly. The book does far better job of drawing these pictures. So I'm just going to use the book here and zoom in on them and see what we do. Okay. Now there's essentially 6 options. You've got you're going to set up a triple integral of f, d something else, d a third thing. I mean, what could you do? You could say, well, I want to put my x out here and then y and z in here, or maybe I want the x out there and then the z and the y, or maybe I want the y out there and I've got an x and a z, or maybe I want the y out there and I've got a z and an x, or I want what's left. It could be a z out there with an x and a y, or a z out there with a y and an x. So there's 6 different options that you have, okay? And these pictures here are essentially helping us through the option. If you got a region that looks like this, essentially it's cylindrical from the point of view of the cylindrical vertically. That is, these vertical sides are essentially flat or just parallel to the z-axis there. And so when you project it down onto the xy plane, you've got this region down here, D, that for each point in that region, you can describe a bottom function that they're calling u1 here, and a top function which they're calling u2. Okay. I want to run, I want to hide. So this is generally the way most people like it. Notice the difference between this picture here, figure 3, and this picture here, figure 4. Maybe if I get them both on the page at the same time. The difference being in that once you've decided that it's kind of vertical in the z direction here and you just project straight down, then there's a matter of, do you have a definite minimum x and maximum x with a big y value and a small y value, or is it better to go this way with a minimum y value and a maximum y value with sort of a minimum x function and a maximum x function? Okay. Each one is different. Okay. The thing is, though, with it, either one of these, the x and the y are on the outside 2 integrals and the z is on the inside integral. Okay. I look at this way. Okay, for instance, on this one, there's an absolute minimum x of a and an absolute maximum x of b, and that's what's on the outside. X is on the outside here, and that's that, right? X from a to b. Then for each value of x in between a and b, I'm looking at what do the y values do. Well, the y values go from here out to there. They go from a minimum of this g1 out to a maximum of that g2. Then, so you've got a value of x, and then you say, okay, so now for each value of y, the z value goes from this minimum u1 up to the maximum u2, and that's what those things are. On the other hand, when you're looking at something like this, the y is on the outside. So this is a dy on the outside. The z is still in the middle, right? So for each value of y between c and d, for each value of y, x runs from some minimum x to some maximum x. So from h1 to h2 here. Those are both functions of y. And then, so for that value of x and some pick a value of y, z goes from the minimum z of u1 up to the maximum z of u2. I want to run, I want to hide. And so you got that, you know, those two things. So the z's in the middle each time, but you've swapped x and y around there. Okay. Other alternatives are, where is it? Next page. Next page. Sometimes it's easier to set it up this way, where you can see that the sort of the cylindrical part is parallel to the x-axis, so it projects really nicely down onto the yz plane. Then you're going to have the option of, you know, is it better to say some minimum y to maximum y, and for each y value in between, you're going from some minimum z function to some maximum. Right, that would have the y's on the outside, then the z's and the x's in the middle, right? Or maybe it's easier to say you're going from some minimum z to some maximum z constants, and then for each value of z in between, you've got a minimum y function and a maximum y function, right? Either way, the x is on the inside, and you're setting up essentially a double integral dA over this d. And how do you set up that double integral? Well, it depends on what that region looks like. And then lastly, you have the option of maybe it projects better onto the xz plane, in which case the cylindrical sides here look parallel to the y-axis. Right? That gets the y on the inside of your integral, and then you're setting up a double integral over this d with the outside two. And again, that's going to be, is it easier to do minimum x, maximum x with a function describing the lower part of z and a function describing the upper part of z, or is it easier to say minimum z to maximum z, come back, with a function describing the small x's and a function describing the large x's? Okay. Let's do an example, and the example